the constant rate of change, while a nonlinear function does not have a constant rate of change. So its graph is not going to be a line.
It's going to be a mountain.
Right, it could be a mountain, exactly. So let's see. Alina was going to walk us through example 1. And it says, does the table represent a linear or nonlinear function, and explain? So Alina, for A, is this one linear or nonlinear?
This one, it is linear because on the top it's plus 3 plus 3 plus 3, and it's consistent. And also on the bottom, it's consistent because it's minus 8 minus 8 minus 8, so it's linear. Perfect.
Yep. So as x goes up 3, y goes down 8. And that happens every time. So this is consistently doing this. So that makes this one linear because it has a constant rate of change. So what about B? Let's see. Julia, do you want to try B?
I think it's not linear because it doesn't have any sort of pattern.
Perfect. It's not linear. Because we can see on the top, x goes up 2, and then y goes up 9, and then it goes up 22, and then it goes up 55. So there's no constant rate of change for our y's. So this one is not linear. Perfect. Yep. Nope.
I have
Abby.
a question.
Yeah, question. Go ahead.
This isn't about the math, but is there a test?
No, we won't have a test in here.
Then why?
I guess I'll give you a test and then we go over it the last
Why
day,
is there
I
all
think.
this stuff?
Oh, it was just extra stuff. I gave Alina some extra stuff for last week. Yeah, it was just if you wanted to do more stuff. But if you did it, Julia, good job. You got extra practice. Abby, this isn't the last class. We have until lesson 15. So after this one, we have 3 more classes. All right. Any other questions?
Is there going to be a final test?
I don't think there's a final. I think there's a final, like, it's like the homework. I'll give you that, the final test. And then when you come back for the last class, I think we'll go over it to make sure you got everything. Does that make sense? Any other questions? All right, perfect. So as we were saying, so B is not linear. Alina, did you have a question? Or did you want to just try A?
The next one.
Yep. Yeah, 1 second. So B is not linear because our y's don't have that constant rate of change. They're going up at just weird, crazy things. So let's see. Example 2 says, does the graph represent a linear or nonlinear function? And then explain. So Alina, you wanted to try A. What do you think? Is this linear or non-linear?
I think it's non-linear because it's not a line. It's like curving.
Exactly. So we can see right here, our rate of change is going up, right? It's almost at infinity. And then as we go, we're getting closer and closer. Now our rate of change here is going to be almost 0 because we're at a flat line. And then we keep going up and up and up, and our rate of change gets up and higher again. Does that make sense? Is that kind of confusing? Does that make sense to everybody else? Julia?
Okay, so it has to basically be a straight line. Doesn't count if it's curved at all.
Exactly. Because when we have a curve like right here, it curves like this. And so as we can see here, if x is 0, y is 0. And then when x is 1, y is, it looks like under 1. It's like right here. But then when x is 2, y goes all the way up to 2. And so then when we get x is 3, it's all the way up here off the map. And so our x will be, right, if we said x is 0, 1, and 2, then our y is going to be 0, we'll say maybe 0.2, and then to 2. And then when x is 3, this is like way up here somewhere, probably around 5. So we can see here, this isn't a constant rate of change. Does that make sense? Perfect. And I think if we wanted to get more technical, I think if you wanted to graph this one, it's an x to the 3rd power. Y equals x to the 3rd. And so this tells us that the exponent of a 3 tells us it's not linear. Does that help, Julia? And everybody else?
How can y equals x cubed if 1 cubed is not 2? 1 cubed is 1.
This is the base formula. And so it's going to be y equals x cubed with some other like stuff, right? So it'll probably be like y equals, let's see, if we put in a 1, we would have to say, I don't know, we could do like 1 over 5 x cubed, something like that. Oops, Nicole's in the waiting room. All right, any other questions or anything? Perfect. So let's see. Andy, can you tell us if B is linear?
I think it would be, but I don't know because the y is steady.
Right, it's always constant.
Yeah.
Yep. So if x is going, right, if we said x is 0, 1, 2, and 3, and then y, it looks like is going to be -2, -2, -2, -2. So it would be linear because this goes up 1 and this changes 0, right? It's just 0. So since that is a constant rate of change, it's no rate of change, it's constant. So that would be linear. Good job. Okay, let's see. So now we have exercise 1. Does the table or graph represent a linear or nonlinear function? And explain. Let's see. Melissa, would you like to try number 1? Is this linear or nonlinear?
I think it's linear.
Linear, and why do you think it's linear?
Because the y and x are going up at a steady rate.
Perfect, yep. Looks like these are going up +7, and these are going down 5 at a constant rate. So it's linear. Good job. Let's see.
Wait, but what happens if one of the values, like one of x, like either x or y, is constant, but then the other one isn't?
Right. So that would be like this one right here. Right, Julia? So do you want to try? Let's see. We have another one coming up. So
That's not linear, I can tell.
number 2?
Yeah, I don't think so.
You don't think so? So you think it's not linear. And why do you think it's not linear?
Because, is that an 8 or a 3?
This is an 8.
Okay, that's linear, actually.
Okay, it's linear.
I thought it was a 3.
No worries. So why would it be linear then?
Because for every 2 the x goes up by, the y goes down by 4, and it's constant.
Perfect, yep, because they're constantly doing the same rate. Exactly, so it's linear. But like you said, Julia, if this 8 was a 3, then our first one would be going up 1, then down 4. So if it was a 3, it would be not linear. But an 8 means it is linear. Let's see. Alina, would you like to try number 3? Is this linear or non-linear?
I think it's non-linear because it's not like a straight line, like a line.
Okay, because it's not like a straight line, right? And we have a different rate of change, right? So if we're looking here at x, and we'll just say from -2, -1, 0, and then 1 and 2. Y, it looks like at -2 is -2. Y, when x is -1, is 0. 2 here, and then we go 1 is 0, and then 2 is -2. So our x is going up 1, and then our y starts off at +2, and then switches to a -2. Or whoops, +2 here, and then a -2, and then a -2. So right here, we have a change in our rate. So it's not constant, which means it's not linear. Good job, Lena. Any questions on these or anything so far? All right, perfect. Let's see. So example 3, it says which equation represents a nonlinear function? So we have 4 choices. Let's see. How about we do this? Thumbs up if you think A is linear. Y equals 4.7. I see 1 thumbs up. What do we think? A, linear or not linear? Linear or not? See 2 thumbs up. Andy, is that a thumbs up?
I don't know because I don't know the x.
Go ahead, Alina. So this is one kind of like this right here, right? So y equals 4.7. If this was 4 and this was 5.
The x isn't consistent, then it's still not linear.
Just disagreeing, but if y has to be 4.7, let's say x is 1 and then 15, x can still be 7.5 in the middle. Because y is always 4.7.
Oh, but like what if x is 1 and then y is 4.7, but then all of a sudden x jumps to 1,000,000 and then it jumps back to like 30? That still isn't constant.
Andy, what do you think?
Then you have to just reword it so that it would go from 1 to 30 to 1,000,000.
Yeah, but you can't just do that.
Can't you reorganize the graph thingies?
Not when it's graphed, right?
So you're bringing up some good points. Let's think about this. Do we know if you have x equals 1, is that a line? Julia?
Yeah.
X equals 1?
Yeah.
Okay, so that would be like at 1, if we said x is 1, there would be a line right here at 1, right? So if y equals 1, wouldn't that be a line right here at y equals 1, like this?
Yeah, but it's because both are the same thing.
Well, they're kind of the same thing, right? One's vertical and one's horizontal. So they're a little different. So if we're looking at this one, y equals 4.7, 4.7 is like about here. So it'd just be a line. So if I told you x was 1,000,000, what would y be?
4.7.
4.7. What if x was 1,000,001?
4.7.
y?
But what if it's like a line?
So this is a line. This is a line right here. And so you can have a graph,
What if
right?
X suddenly jump? But then you have to make it keep going.
Yeah, all lines keep going. And
Like you need to make the graph bigger.
Well, it doesn't matter. You don't need to, because we know that y is always going to be 4.7. So if this is our graph, if I said this was 1 million, right here, this would still be going, and we would still be y at 4.7. So no matter how many x's you go up, if I went from x from, let's see, this would be 500,000, and this would be 250,000, and this would be 750,000. So if I said x went from 250,000 to 500,000 to 3/4 to 1 million, right? We could say this is a constant rate of 250,000, and and then y is always going to be 4.7. So at all of these points, we will still have 4.7. So x isn't changing. It's at a rate of 0. But that's a constant rate. Does that make sense, Julia?
Okay.
It's like this one we did right here. Does this one right here make sense why it's linear?
Well, because I can see the line there.
Right. So this line has the graph, or has an equation at y equals -2. That's this graph's equation, right? Now, if we're going back down to this one, this is y equals 4.7, right? So now instead of being at -2, this line is just going to go up to 4.7, but it's still going to be the same. It's going to be all the way across. And so we can see that no matter how, we can, if x goes up 1, this goes up or down 0, right? It just stays the same. Does that make sense?
Okay, so if at least one of them is the same, then it's always linear.
Well, right. If y equals something without x, and if x equals something, they're going to be linear. Because no matter what, there shouldn't be a weird change anywhere, because y is always going to be 4.7. Nothing can change that. So it doesn't matter what x is. So what about b? So this one is linear. So what about b? Do we think b is linear or not linear? Thumbs up for linear. Thumbs down for not linear. All right, Julia, you have a thumbs up, it looks like. So,
because like for every one that x is, for every one x goes up by y goes up by pi.
Perfect, exactly. So if x is 1, y should be pi, and then 2 pi, and then 3 pi. So these are constant rates. So b is linear, exactly. Great job. So what about c? What do we think? Linear or not linear? Does anybody know what this one looks like, the graph for this?
Like x times 4 is the y.
But it's 4 divided by x. So it's weird. It's a weird one. That's okay. here's what it looks like. So it comes straight down. Here's our X and Y. And so it actually looks something
so X
like.
times Y is 4, right?
So X times Y is 4. That's right.
I don't think that's linear.
So it's not linear. You're exactly right. This is not linear. Here, and I'll show you the graph real quick. So it has an asymptote at 0. And so it can't be 0 because X is in the denominator. And so if X can't be 0, Y can't be 0. Because if Y is 0, that would mean that this whole thing is 0. But we know X times Y is 4. So if any of them are 0, then we have a problem. So this one's kind of weird. It comes down and does this, like this. But it also has the same over here. So that's what this graph looks like. This is Y equals 4 over X. It looks like this. So we can see.
It looks like art.
It looks like art. kind of like art. So we can see here, right? If we're like way down here, we have like almost a 0 rate of change. And then it goes way down. And then it goes way up and then way down, right? So this is all sorts of not linear. And so what about, so then it says which equation? So we found the one that's not linear. So D has to be linear. And we can see here that if we have Y equals 4X minus 1, I like to change that to Y equals 4X minus 4 by distributing the 4. And so then if we have X is 1, 2, and 3, we can see Y is going to be 0, it looks like. 2 times 4 is 8. So 4, 12 is 8. So it goes up 1 and up 4. Perfect. Does that make sense for everybody? Any questions, comments, or concerns? Okay, perfect. Let's see. Example 4. Account A earns simple interest and account B earns compound interest. The table shows the balance for 5 years. We have to graph the data and then compare the graphs. So let's see. Let me put it this. So we'll do A over here. All right, and then we'll say 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. What do we got? Up to 150. So if this is 100, 10, 20, 30, 40, 50. Oops. And then 160. Okay. So we're going to graph these. At 0, we have 100. So I'm going to say 0, 100. And this is A, and this one's B. So 0, 100, 1, we go to 110. 2, we go to 120. 3, we go to 130. 4, 140, and 5, 150. Oops. Then if we look over at this one, it starts out the same, 0, 100, and then 1, 110. But then we get to 3 or 2, whoops, and 121, 3 and 133, 4 and 146. And then we get to 5, we get up here to 160.
I don't think account B has any sort of pattern to it, and it's not linear.
Perfect. This one's not linear. And this one's linear. And so we can see here that this linear one, it grows at a constant rate, right? While this nonlinear one does what Julia says. It doesn't really have a constant rate. It's doing this weird stuff. But we can see that this one is going to start getting a higher rate. So if we wanted to earn more interest, we would want to put it into B, because that would give us the most money after 5 years. Does that make sense for everybody? Perfect. Any questions, comments, concerns? All right. So exercise 2 says, does the equation represent a linear or nonlinear function? And explain. Let's see. Does anybody want to try A? Andy, what do you think? Is A linear or non-linear?
I can do it.
I think it's linear because the +5 just means it's moved up 5, so x would equal y.
Exactly right. So that's a good call. So Andy noticed that y equals x is just like this. And if you add 5, it just goes up 5. And so it's still linear. Great job, Andy. Nicole, did you want to try B?
Yeah.
Okay, perfect. What do you
So
think? Linear or non-linear?
I think it will be non-linear because every time C4's x is different.
So we got to be careful. What if, here, we'll draw this. If x is 0, 1, 2, and 3. And then we'll say y. So if x is 0, y should be 0, right? If x is 1, y should be 4/3. And then if x is 2, y should be 8/3. If x is 3, this should be 12/3. So if we look at this, Nicole, it looks like x is going up +1 every time, and y is going up 4/3 every time. Doesn't it?
Yeah.
Yeah.
Thank you.
So this one's linear. That's all right, though. It's okay. Because this one's kind of tricky. We haven't seen one like this yet. This shows us that 4/3 is our m. That's our slope. So that tells us that it is a constant slope. All right, Julia, do you want to try C?
Okay.
What do you think? Linear or non-linear?
I don't think it's linear.
You don't think it is?
I don't think so.
Okay.
Because different numbers have different squares depending on how big or small they are.
Okay. So a good one for this, right, is if we did say, what would this be? Negative x plus 1. Okay, so if we did x being -1, 0, and 1, if we said y, if x is -1, that would be -1 squared, which is 1, and 1 minus 1 is 0. If x is 0, y is 1. But what we said, if y is 1, that's 1 squared, we get 0 again. So here, we're going up 1, up 1, up 1. And right here, we go up 1, but then we go down 1. So our rate changes. And so this one will look something like this, right? And so it's not linear. Great job. And actually, I think I have them right here. And so we can see this one's not linear as it goes all the way down. And then here are our other two. Here is A, B, and C. Any questions on those? Comments, concerns? Easy stuff for everybody? All right, perfect. So now we're going to look at analyzing and sketching the graphs. our key idea here says that graphs can show the relationship between quantities without using specific numbers on the axis. So we can see here, if this is our time and here's the distance, we start by increasing our time and distance, and then our distance stays constant with time, and then we get a lower distance as we get closer. So increases over time, and then it's constant over time, and then decreases over time. Does that make sense for everybody? Perfect. Alina, do you have a question? Do you want to try the next one?
Try the next one.
Okay, perfect. Let me scroll down here. So example 1 says the graph shows the temperatures throughout the day in 2 cities. So Alina, for A, describe the change in temperature in each city. So this one's Belfast, Maine. What's the change in temperature for this one?
Well, the change in temperature, so it like starts in the lower part and then it increases, then like till it's increase like way at the top, like about at the top, then the temperature decreases at the end of the day.
Exactly right. And so what about Newport, Oregon?
In Newport, Oregon, so the temperature starts high and then the temperature decreases probably like at lunchtime or in the morning part. And then it is like horizontal, so it's like the same temperature after it decreases. And at the end of the day, the temperature increases again.
Perfect. Great job, Lena. Thank you. That was great description. So let's see, Julia, can you make one comparison from the graphs?
Well, Maine is raising and lowering temperature constantly, but like Origin is more sudden to start changing or going this way or that way.
Perfect. And this is more constantly. And this one's more abrupt. Perfect. Those are 2 good ones.
Well, by abrupt, I don't mean like it just become cold and then like in 1 second it became really hot, because it still is like has slope and all that. It's just that it's not always changing.
Right. It's kind of, it hits a
just
point.
Stops and then it starts changing suddenly.
Right. So it's an abrupt change. That's what that means. It's like it hits a point and then the slope changes. Versus like this one, it like slowly, it's like it's an increase and then it slowly is getting smaller, and then 0 and then lower.
But Maine is always changing, but Origin sometimes isn't changing.
Right. So that's another good one. So like the temperature, this one has a spot where we have a temp constant. And this one looks like it touches that, but it doesn't really stay up there. So this one's always a temp change. So there's 2 good ones. Can we make any other comparison? Does anyone else have any ideas? What do we think? No other thoughts? Anybody? Melissa, Nicole, Abby, Andy? Any other comparison for the graphs? All right, no worries. I'll make one. How about this? Can we say that Maine actually starts off colder than Oregon and ends colder, versus Oregon starts off hot and then eventually gets a little bit warmer near the end of the day? All right. Any questions, comments, or concerns on that? Okay. Perfect. Let's see. Oops. Up in here. Like that. All right, there we go. That's better. All right, let's see. The graph shows the paths of two birds diving to catch fish. Describe the path of each bird. So A says, describe the path of each bird. Let's see. Alina, since you did A last time, we'll let somebody else do it. And then you can help us make a comparison.
Okay.
Let's see. Andy, do you want to help describe the path of each bird?
Okay. So for the first one, it starts up high and then it drops down. And then so it's a pretty steady rate until like the middle.
And then
And
drops
then
fast.
it's another steady rate at the bottom, like I mean, not steady rate, but steady slope.
Perfect. Okay. And that's for the pelican?
Yep. And
What
then
about-
for the other one, it's very fast. It goes down and goes down more.
Perfect. So it starts diving, hits a spark, and then dives even further.
Yeah.
Perfect. Yep. And a pelican's more of like he swoops in and it's all
Yeah,
nice.
it doesn't even. I think the osprey ends up below, but it doesn't look like the pelican really touches the water.
Yeah, it looks like it might touch the water eventually at some
What
point.
if that's not
below.
water? Then the osprey would end up hitting the ground face first. If that were water, and if it were water, it would end up hitting the water. But the pelican is more like picking up its prey at the end, I guess, and then continuing flying.
Yeah, probably. That sounds about right. And so there we made some good comparisons, right? So we made one comparison that the pelican probably isn't going to hit the water like the osprey. It might just touch the water and keep on going, where the osprey is going to dive right into it or into the ground, whatever it might be, right, Julia? Any other comparisons? Alina, did you have any comparison?
Well, I did notice that both graphs started, like both birds started very high, like they were flying very high, and like they like went down to catch their prey.
Perfect. Yeah. So they're both like similar in a way because they both start off high and decrease and then almost hit the water or hit the water. So that's exactly right. Anything else? Any other comparisons? Does anyone else have any ideas?
Well, I think this is one, I don't know, but I noticed that both graphs are starting from, like both birds are flying from the left. I don't think this is one, but I'm just noticing both graphs are starting from the left to the right.
Yeah, that's just to make everything easier so we can see, because we don't want to go into a negative horizontal distance, because if we have negative distance, then it's just going to get all sorts of weird with our math.
Oh, and this isn't related, but it is water because it says they're diving to catch fish.
Perfect. Yep.
I have another one.
Okay, what else?
So I noticed that the pelican is like going up to down, like kind of wavy. The line's kind of wavy, and the osprey is like sharp, and it goes like up and then sharp down.
Mm-hmm. So the osprey is diving fast, and then he hits a point, and then he dives even faster. Where the pelican is kind of diving, and then he hits a part, and then he almost dives straight down, hits a part, and then almost glides back up. And like Julia said, probably just catches some water in its beak or some fish, and then keeps on flying off. Where the osprey is going to go straight into the water to try to get its fish.
And it's going to take a swim.
And it's going to take a swim for sure. All right. Anything else on this one? Any other questions or anything? Those were all really good answers. Nicole, question?
If you look at the general shape of the Oscar and Pincher, they seem to look the same. Like, how can you tell if the Pincher didn't suddenly turn down?
How can you tell that it suddenly turned down?
I mean, like the other bird didn't.
Oh, the pelican? So this is, it's a vertical distance, right? So that's how high we're going. And so here, let me erase some of these marks and see if that'll help. And so what this is saying is that as we're going this way, right, over a certain distance, the bird's starting off in the air. And so if we have like a little bird here, it's flying, right? And it's kind of hungry, so it wants some fish. So it's just kind of barely flying along this line. And then it hits a point and it has to go straight down. And so it drops vertically from here to here, but horizontally, it doesn't really move much, right? It's going like straight down. And then it hits this part, and then it basically just goes all the way to the right. So that's how we know it goes straight down. Does that help?
Yeah, thank you.
Okay, perfect. Yep. Any other questions or anything? That was a good question. Okay, we'll move on to the next one.
Can I do A?
Yeah, you can try A, Julia. Let's see. Let me read the key idea and such, and then you can go for it. Let's see. This says you can sketch graphs showing relationships between quantities that are described verbally, kind of like we did, but opposite. So it says sketch a graph that represents each situation. So Julia is going to do this. It says A stop subway train gains speed at a constant rate until it reaches its maximum speed. It travels at this speed for a while, then slows down at a constant rate until coming to a stop at the next station.
Oh, I made a mistake.
Can I do
have,
B?
Is that Alina?
Mm-hmm.
Let's see. Okay, yeah. So here's A and here's B. So let's see. Elena, can you do it on here, on this graph right here? And then Elena, you can do yours here. Yours says, as television size increases, the price increases at an increasing rate. And so first thing we'll have to do is, Julia, this will be the speed side.
I think you just called Julia Alina.
Oh, whoops, sorry. Julia, you have this side. And so speed and time. And then Alina, you have this one, and we want, this will be price, it looks like.
Mm-hmm.
And this is TV size.
TV size. Wow.
Perfect. All right, Julia, walk us through yours.
Okay, so basically, And first it says it's gaining speed at a constant rate here until it reaches its maximum speed. And then at the top, it just stays at the maximum speed for a while, but then it constantly slows down until it doesn't move anymore.
Perfect. So right here at 0, 0, it has no speed and no time. And then Julia did a good job. It has a constant speed. Hits its max and then goes at its max speed until it hits a certain time and then drops down, then gets to the next station and stops again. Great job, Julia. All right, Elena, you want to walk us through yours?
So basically my line is going from like kind of partly middle, partly down. So it's kind of like in the middle, and it's increasing because it says as television size increases, the price increases at an increasing rate. So the TV size is like increasing and the price is increasing as well. So like it's going up.
Perfect. Exactly right. And so if we were increasing at a steady rate, it would be like this. But since we have an increasing rate, it's like Alina showed, where it's going to go like this and then go up like that. So that's exactly right. Great job, Julia. Great job, Lena. Let's see. Oops. Get rid of these.
I have a question for the battery one. It says you plug it in and recharge it fully, but doesn't it take time to charge a battery? But I don't know how much time it is because it depends on how high voltage your charger is and what kind of battery you have.
It does. So we're just looking at the math. We're not going to look at all of the details. We're not going to look at the numbers part. What we're worried about, Julia, is just what the graph looks like and if we can make something based off of what they give us. Does that help?
I don't think it's very realistic that the second it loses its charge, you would recharge it.
So let's look at this one. Sketch a graph. So a fully charged battery loses its charge at a constant rate until it has no charge left. Then you plug it in and recharge it fully. Then it loses its charge at a constant rate until it has no charge left again. So if this is time over here, and here is our charge, we'll just say that this line here is like a full charge, right? So we're fully charged battery, loses its charge at a constant rate. So it's just constantly losing it. We hit a part right here. Then it has no charge left. And for the sake of being a battery, Julia, we'll say that for like a little bit of time, it was like dead. And then we plugged it in. And then we will say it recharged at a constant rate too, right? So we'll just do this. So then it increases at a constant rate until it recharged fully. And then we unplugged it. And so now it loses its charge again all the way until we hit 0. Does that make sense, Julia?
Okay.
Is that what you were thinking?
Yeah. I was
Okay,
just
perfect.
wondering how fast it would charge because it really depends on what kind of charger and battery you have and how long you wait until you start charging it.
Yeah. So what we could say is if we plugged it in at this point, it became fully charged here. And so we'll just call this distance the time X, right? It took X amount of time. We don't know the number, but it was a certain amount. Does that help? Okay, and so B says, as the available quantity of a product increases, the price decreases at a decreasing rate. So if here's our price again, And then this is product, available quantity of a product. And so at the beginning, we had a bunch of product, right? And then we started to decrease in product. And then it started to decrease really, 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 really fast until we hit nothing. Something like that. Does that make sense for everybody? Any questions on that one? Perfect. All right, I see some thumbs up. Good. Any questions, comments, concerns?
How come B is a loopy?
Because this one says it is decreasing at a decreasing rate. And so our straight line has a decreasing rate that's constant. But when we have a rate that's decreasing or increasing, it'll be like it slowly does it, and then it gets a little bit bigger, 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 bigger until it's like all the way straight down. Does that make sense? Okay, perfect. All right, any other questions or anything? That was a good question, Julia. So we've come to the homework part. So why don't we look at a couple of these? Let's see, 270, 271.
Can we do more graphing?
You want me to look up a couple graphing ones? Let's see. All right. Julia wanted a graphing. Let's see, 270. Okay, let me see. Oops. 1, 2, 4, 6. Okay. Sure. All right. Can everybody see this? My problems? So we see number 7 and number 8. Let's see. So what do we think? We'll draw. For number 7, do we think this one's linear or non-linear?
Linear, and the second one is non-linear.
Linear because it's a line, like a straight line.
Perfect. Yep, it's a straight line. And this one's non-linear. Why do you think this one's non-linear?
It's not a line. It's like a squiggly kind of stuff.
Yep, right here we got some weird squiggle stuff happening. So that one's definitely not a line. Good job. Let's see, let me find a harder one maybe. So interpreting a graph. Okay, here we go. Here's a good one. We're going to match each situation with the appropriate graph and explain our reasoning. And so this one already gives us words and we can put it to the graph. So maybe that'll be nice. Let's see, what do we want? Let's go with pink. All right, so A says you gradually increase your speed, then ride at a constant speed along a bike path. You then slow down until you reach your friend's house. What do we think? Is this one going to be A, B, C, or D?
C.
So I heard a C.
C.
I see some couple hands up.
C.
What are the people with their hands up? Melissa, what do you think?
I think it's C.
C? All right. So we got we'll write a little C next to this one, and we'll say A. And so if we look here, we gradually increase our speed, and then we ride at a constant speed, then we decrease until we reach our friend's house. Perfect. So that one looks right. What about for the next one? You gradually increase your speed, then go down a hill, then quickly come to a stop at an intersection. Part B, what are we thinking? A, B, or D?
B?
So I heard a B.
Actually, well, I think it's either A or B because I think D is like, I think
Maybe D.
So we heard I heard a D.
You gradually increase your speed, so it could be A or D for the.
no, I think D. I think D is C.
Hmm?
I think C is D. Like
This
because you increase your speed, then slow down, stop, and then continue. So it can't be D. So it's either A or B. But it can't. But then again, it can't be B because if you came to a stop at an intersection, why would you keep getting faster? But then it does make sense why it would be A for D.
So let's look here. Let's see. Some of these are a little hard because they feel like they don't have. So let's look at C. Look at this C. It says you gradually increase your speed, stop at a store for a couple minutes, then continue to ride, gradually increasing your speed. So this one tells me that I gradually increase my speed. Then I have to slow down to stop at the store. I'm in the store and then I leave, right? So I'd say C goes with this D.
Oh, I found it out. I think I got it now.
All right. So you think you got B, Julia?
No, I think I got D.
This D? All right. So let's look at this.
I think D is B because if you're riding at a constant speed, B begins at like I don't know slow. But then when you go up a hill, you naturally get slower, so the speed drops. But then it says you gradually increase your speed. So D is B, and I mean B is A.
Perfect. And so let's look at this one. Look at D real quick.
I think I got mixed up because I thought of the speed as like what the hill looked like.
Yeah, no worries. So let's look at this one. So we ride at a constant speed. So we stay at this speed. Then we're going to go up a hill. So going up a hill, we slow down because it's too hard to pedal. Get to the top of the hill. And so now we're going down and our speed will increase. And so if we're looking at B, this should go with A. So we increase our speed. Then we hit the top of a hill. So our speed gets even higher. Then we got to come to an intersection. So really, really fast, we have to slow down. Good job, everybody. Did that one help? Is that a pretty good one? I think that was a pretty good one.
I want more like that.
All right, let me see what I can do. What about these ones? Do you like these ones? How are these graphs similar? And how are they different?
They go up, and one is curvy and one is not.
Perfect. So they're increasing, right, in their rates, but B has a constant increase while A has a curved increase. So it's an increasing rate. To
compare the steepness of A doesn't really go up much, but then it goes up more, and B just gradually goes up.
Right. So B has the same steepness. It'll stay constant. And A increases its steepness, and then it'll become super steep.
I think A is the thing of the rocket because you need to accelerate before you can go really high.
Yeah, so this says high above the ground in time. So yeah, it probably starts off and it starts to go and go and go and slowly goes up. I would say A. I would agree, Julia. Let's see. Working with partner, speed of 2 cars. This is the same, just opposite. Okay, let's see. Those are the ones we just did. Oh, we did those ones. Okay, here we go. This looks like it's a good spot. So this says, to match the verbal description with the part of the graph it describes. So where does it stay the same? Julia says F stays the same. That looks good to me. Slowly decreases at a constant rate. We said D. Okay, I could see that. Actually, got to be careful with this one, I think. Slowly increases at a constant rate. Yep, so this is right, increases at an increasing rate. So it starts to get bigger and then eventually goes way up. And so what about this? Slowly decreases. There we go, C, because it's slowly doing it. Slowly, yep, so A, it's going up, but it's not going up super fast. So quickly would be D and B, because it shoots up really quick. It's almost super steep. Does that make sense for everybody? Any questions on those ones? Perfect. All right, let's see. All right, how about this one? Number 13. This looks like a good one. This says the graph shows the natural gas usage for a house. So we can see it here. Here's the months and here's the usage. So describe the change in usage from January to March. Oops. Oh, what's happening? There we go. Okay. Let's see. From January to March, what do we think? So at January, it looks like we were here, and at March, we end up going here. What do we think? Any ideas? Looks like our usage in January was super high, is what I would say. And then it decreased when we got to March. And then, Alina, what do you think? From March to May?
From March to May, so it looks like it's like decreasing. It's not like decreasing very fast like this, but it's kind of like this, like a hill.
Perfect. Yep. So it's not like a super fast decrease, but it's definitely a decrease that we can see. Good job. Let's see here. Ooh, that looks like new stuff. We can't go too far into that. All right, let's look at this one here, this big colorful one. All right, so looking right here. If we're looking at this one, here's our X's and here's our Y's. What do we think? Is this one going to be linear or non-linear? What do we think? Any ideas?
Non-linear.
So
Because
Julia says non.
Is does have a pattern from red to yellow, but I feel like it's just getting random after that.
Yeah, so it looks like, I think the same thing, Julia. It looks like there's some sort of pattern from here to here. And it looks like it's 65, right? You're losing 65 all the way across. But then when we look at the y, it looks like we increase 50. But then here it looks like we increase by 62. And then right here it looks like we
But didn't you say if something is the same? Oh wait, never mind.
It has to increase the same amount, right? So from here to here,
it was like if it stays the same amount.
Yeah, so if it stays the same amount, it still is linear. But you're right on this one. This one is non-linear because these y's are doing some weird, it's not a constant thing. It's a weird thing. Let's see. Good job, Julia. Let's see. All right, what about this one here? Look at these 5 here. Let's see. Change the blue. What about this one, number 2 right here? It says, which equation does not belong with the other 3? And explain your reasoning. So we'll have A, B, C, and D. So can anybody tell me which one of these doesn't belong? A, B, C, or D? We got 5y equals 2x, y equals 2 over 5x, 10y equals 4x, and 5xy equals 2. Andy, what do you think?
D.
Andy thinks D. We got 1 vote for D. Alina, what do you think?
I think it's D too.
Okay, we have 2 for D. Julia, any ideas? Melissa, Nicole, Abby, any ideas? A, B, C, or D?
Yeah, I think it's D.
Okay. Nicole, what do you think?
I think it's probably D.
Okay, perfect. So let's see. Let's see why it could be. So 5y equals 2x. What I want to do is try to get it like this, where y is by itself and x is by itself. But y is isolated. So if I divide it by 5 and divide by 5, this would turn into y equals 2 over 5 times x. So those are the same. And then if we did the same for c, divided by 10, y equals 4 over 10 times x. 4 over 10 can be simplified to y equals 2 over 5 times x. So those 3 are the same. So that just leaves D. And that's because if we try to divide it by 5, we get xy equals 2 over 5. But we also want to get rid of x. So we divide it all by x. And then we get y equals 2 over 5 times x instead of 2 over 5 times x. Now x is on the bottom. Does that make sense for everybody? All right. So we're going to look at these 4. And just by looking at these 4, we're going to tell if they're linear or non-linear. We're not going to graph them, okay? Let's see. So number 3, we're going up 1 for x's. And then for y, do we have any constant rate, any constant change? What do we think? Any ideas? Alina, what do you think?
Well, since the top is constant and also the bottom is constant because it starts with 4 and then 8 and and then 12. So it's basically like adding 4.
Perfect. So for every 1 x we go up, y goes up 4. Exactly right. What about this one, number 4? It looks like we still go up 1 for our x's, but our y looks like it goes up 1 and then 4, and then it goes up 18. So is this linear or non-linear? Oops, this one's linear. Anyone else? Julia, what do you think for 4? Think this is linear or non-linear?
Non-linear, because first it's just when x is going up, while y is also going up 1, but then later after the third one, it starts going like +3, and then it goes all the way to +24.
Perfect. Exactly right. Let's see. Alina, what about number 5?
So the top is constant because it's constantly subtracting 1. The bottom is, I think the bottom isn't constant because it's like subtracting 6 and then subtracting 5 and subtracting 4.
Perfect. Yep. So it's non-linear, right? Because we don't have that constant change on the bottom.
Mm-hmm.
Perfect. Good job. All right. Let's see. Andy, do you want to do number 6?
Sure. So it starts at -1, it goes up 0, goes up and adds 4 for the y. Then it goes up 1 and adds 4 again. So it's a linear equation.
Perfect. Yep. So we go up 4 every time on the y and 1 for our x's. So this one's linear. Great job. All right. So any other questions or anything? Was that some good extra practice, Julia?
Sure.
Sure. Just sure. Okay. All right. Did you want some more?
No.
Okay. All right. Are you getting tired of math?
Yeah.
I don't blame you. It's okay. A lot of math in one day. I'm sure you had more math at school today too. So I completely understand.
I can like do easy math for a long time, but I just get tired of doing hard math after a while.
It hurts your brain.
Not like easy math is fine, but then like math that you don't need to solve in like 2 seconds is tiring.
I know what you mean. I feel you. All right. Well, I tell you what, since that's it, we went through a lot of stuff and we did a few of the homework problems too. So I'll let everybody go early today. How does that sound?
Can we do a few more problems together?
Yeah, I tell you what, Alina, if you want to stay on, if everyone else wants to go, that's cool. And I'll stay on and do some more problems if you want to stay on. How does that sound? But if you don't want to,